In this episode, I want to talk about some very abstract concepts, starting off with the notion of external direct sum. To motivate this, consider the space R3. So R3 is going to consist of all elements of the form a, b, c, where each a, b, c is a real number. But looking at this, you should realize that R3 is really composed of a, b, which is really coming from R2, and c, which is just coming from R. To make this more explicit, you can think about a, b, c as a tuple just consisting of two numbers, the first being a, b from R2 and the next being c from R. And how we can express this decomposition is that R3 is equal to the external direct sum of R2 and just the space R. We can immediately generalize this to any vector space. So if we have a vector space V and W over a field F, then we can simply define the external direct sum V plus W to be the space where now we have a tuple of V, W, such that of course V is coming from V and W is coming from W. And of course, we're going to let the addition and scalar multiplication be done component-wise. So for example, A times V, W is going to be AV, AW, and so on. On the other hand, we can define the notion of internal direct sum. And to motivate this, now realize that R3 can be decomposed into R2 plus R in a different way. Namely, if we have R3 that looks something like this, then we can naturally think of this xy plane as R2. In addition, we can think about the z-axis as being R. And now each tuple a, b, c can be thought of as something in R2, namely a, b, 0, plus something in R, namely 0, 0, c. So in this way, once again, we're going to use the same notation for internal direct sum. We are going to have that R3 is R2 plus R. So to generalize this, for any vector space V and W over a field F, such that V and W are subspaces of U, say, just as R and R2 here are subspaces of R3, then we really want to define V plus W to be the space of all V plus W's, such that V is in V and W is in W. But we're going to require one thing. Realize that when we are splitting a, b, c into something in R2 and something in R, this decomposition is unique. And we're going to require this in our definition of internal direct sum. And how we can do so is by requiring V and W as subspaces or essentially linearly independent. What I mean by this is that if V plus W happens to be 0, then this happens if and only if V is equal to 0 and W is equal to 0. I'll leave it up to you to quickly check that this indeed gets us this nice unique decomposition and proceed to ask the obvious question. Why are we using the same notation for the external direct sum and internal direct sum? Well, it's not too hard to see for this particular example because really this a, b corresponds to a, b, 0 and this c corresponds to 0, 0, c. But even in general, not just R3 being decomposed into R2 plus R, if you consider the spaces V and W satisfying these properties right here, and you consider the external direct sum and the internal direct sum, we can immediately find an isomorphism that simply sends V, W to V plus W, observing that this map is obviously surjective, and it's injective because for us to get 0 here, then by this requirement we must have that V, W was 0, 0. Now let me quickly add here that an isomorphism like this is often called, at least informally, natural, in the sense that the isomorphism doesn't involve any basis, any explicit choice of basis. To illustrate what I mean by this, consider the algebraic dual space V dual given by the settable homomorphism from V to the underlying field. This is in fact a vector space because when you add two linear maps, you're going to get a linear map, and when you scale a linear map, you are going to get a linear map. So you have vector addition and scalar multiplication nicely defined here. And something interesting to realize is that when V is finite dimensional, the space V dual is isomorphic to V. And how you can check this is by first picking a basis of V. So say V1 to Vn is a basis of V, and then considering a linear map from V to V dual. So once again, we call this the algebraic dual space of V. And considering the map given by sending each basis V sub I of V to the map that simply sends Vi to 1 in the field, and for the rest of the basis elements, So for anything other than v sub I to 0. And it shouldn't be too hard to see that this map phi is in fact an isomorphism. For example, phi is surjective because anything in V dual is really given by sending each basis VL to something in the field, say A sub L. And we can get exactly this arbitrary map in V dual by simply inputting the vector sum of A sub L times V sub L into phi. And then this thing is exactly going to get us a linear map that does what we want. I'll leave it up to you to check the injectivity. But the main point is that this map is an isomorphism, but it is not a natural isomorphism, because we had to pick a basis in order to define this isomorphism. Since we're in the topic of dual and natural isomorphism, of course I have to show you the notion of a natural isomorphism of V with V double dual. So now if you consider the double dual of V, so I know this is getting abstract, but try to follow. This is going to be the homomorphisms from the V dual, which is homomorphism from V to F to the field. And for this, I claim that you have a really nice, beautiful isomorphism given by sending a vector V to the map. So now I have to give you a map in this V double dual. And this map is going to take something in home V, F as the input, so something in V dual as the input, and it should output something in the field. And how we can do so is by simply applying phi to V. So we can simply return phi V, and because phi was in home V, F, this thing is going to be an element of the field as we desire. And to see that this map, now let's call it psi, and I guess I should specify that this phi here and this phi here are in no ways related, of course. But anyway, calling this map psi, to see that psi is in fact an isomorphism, I want you to first realize that psi has to be injective because the kernel has to be zero-dimensional. If you have something non-zero that you're starting off with, I claim that this cannot get mapped to the zero map in V double dual. And to see this, just realize that there is something in V dual such that phi prime of V is not going to be zero. This is simply because if you have a non-zero vector V, then we can throw in some, say, V2 prime that's outside the span of V, and then we can throw in some V3 prime that's outside the span of V and V2 prime, and then throw in V4 prime that's outside the span of V, V2 prime, and V3 prime, and so on until we get to some Vn prime, making this entire thing into a basis of V. And once we have a basis of V, we can just consider the map phi prime defined by sending V to 1 and all of these to zeros. And then this certainly satisfies our condition that phi prime of V is non-zero. And what this is telling us is that if you consider this map here, then non-zero V is being sent to, this map in particular is going to send a phi prime to be something non-zero. So what that's telling us is that a non-zero vector V is not being sent to the zero map via psi, implying that this map is injective. And the beautiful thing is we don't have to check surjectivity because for finite dimensional V, we already know that V and V dual are isomorphic. In other words, they have the same dimension, which of course implies that V and V double dual have the same dimension, meaning that by rank nullity theorem, we know dimension of V double dual is equal to dimension of V, which is equal to dimension of kernel of psi plus dimension of image of psi. And since we already know that psi is injective, we know this thing is 0, which means we know dimension of image of psi is exactly dimension of V double dual, meaning that psi is surjective. And I guess here we were just implicitly assuming that psi is in fact a linear map, but that's not too hard to check, and I'll leave it up to you to check it. Anyway, we have shown that psi is in fact an isomorphism, and it's a natural one at that. In the definition of psi, we do not have to pick any basis like we had to over here. Okay, we're going to see example of at least one more natural isomorphism in the series, but for now I want to move on to the notion of quotient space. For this, I want you to first remember the number system like G mod 5Z. And in case you've forgotten, G mod 5Z is essentially obtained by considering the multiples of 5 to essentially be 0 with respect to addition. What I mean by this is, for example, if you do something like 3 times 4 and you get 12, well, 12 is essentially 2 plus 10, and since 10 is a multiple of 5, we essentially think of it as 0, so we say 12 is equal to 2. Or in other words, 3 times 4 is equal to 2, and we usually say mod 5. in the context of vector spaces, now we're going to do exactly the same thing. So if W is a subspace of V, then we're going to now consider V mod W, where anything in the subspace W is essentially going to be considered 0 with respect to vector addition. So that if you have something in V and you're adding something in W, then you're essentially going to consider something in W to be 0. So you're going to write this as equal to V, and we're going to use the notation mod W. More rigorously speaking, we're really saying that V1 and V2 in V are equal to each other in the quotient space if and only if we can go from V1 to V2 or vice versa using some element in W. So there is some W in W such that V2 is equal to V1 plus W. And I encourage you to pause here and check that this equality here in the quotient space does have all the usual properties that you may expect, such as reflexivity, symmetry, and transitivity. To consider an example, if you once again consider the example of R3 and the subspace R2, so here R2 is the xy plane, then any a, b, c, once again, can be decomposed as a, b, 0 plus 0, 0, c. And since a, b, 0 is in the xy plane, we are going to consider this thing to be 0 in the quotient space R3 modded out by R2. So we know this thing is going to be 0, so we're going to have that a, b, c in general is going to be equal to 0, 0, c mod R2. And it shouldn't be too hard to see that under this definition, R3 modded up by R2 is isomorphic to just R, where the isomorphism is simply given by sending 0, 0, c to C. But here, before we move on, there is something about the quotient space that we really need to verify, and that's that vector space operations are well defined. What I mean by this is that if you are considering V1 mod W plus V2 mod W, we want this to be defined to be V1 plus V2 mod W in the quotient space. But a potential problem that we may have is that V1 mod W is really the same as V1 plus some arbitrary element W1 in W, and V2 mod W is really the same as V2 plus some arbitrary element in W. We need to ensure that V1 plus V2 mod W and V1 plus W1 plus V2 plus W2 mod W are actually the same. But of course this is true because W1 and W2 are considered zeros, so that these two are actually equal. So there's no problems with defining vector addition like this, and analogously, I encourage you to check that there's no problem with defining scalar multiplication in the natural way. Now there's a really beautiful observation that I want to make. Suppose that we have a linear map of vector space homomorphism from vector space V to vector space W. And here of course kernel of phi, which are all the vectors that get sent to 0, is a subspace of V. And here I want you to once again realize that if V1 and V2 are getting sent to the same element, W, then V1 and V2 are really the same element modded out by kernel of phi. This of course follows because since V1 and V2 are getting sent to W, V1 minus V2 is getting sent to 0. Which means if we write V1 as V2 plus V1 minus V2, then this entire thing is at 0 because it's in the kernel, so we do indeed get V1 is equal to V2 mod kernel. And this intuition is hopefully enough to convince you that if you modify phi such that now we have the domain of V mod kernel of phi, and we're going to W, such that the map is defined in terms of original phi, where we're sending V to phi of V, this map being well defined because of the observation that we just made, and realizing that this map is now injective. And the reason that it's now injective is because if two different elements were getting mapped to the same thing, now we crushed these V1 and V2 to really be the same element modded out by kernel of phi, and now we're sending it to W. So now that these two elements really just one element, this really forces the map to be injective. And in addition to that, if we make one more modification by changing the codomain of phi instead of W to be image of the original map phi, then we see that this map is now surjective as well. So that we now have a natural isomorphism. So this is a natural isomorphism from V mod kernel of phi to image of phi. And this is such a beautiful observation because think about what dimension of V mod W has to be if V is finite dimensional. If dimension of V is finite, then you really would intuitively suspect, at least from this example, that dimension of V modded out by dimension of W is really going to be dimension of V minus dimension of W. because anything in R2 here in this example are becoming zeros. So the only dimensions that are left is going to be 3 minus 2 or 1. One easy way of checking this, and let me just sketch the proof for now, is to force some connection between the basis of W, the basis of V, and basis of V mod W. And how we can do so, since W is a subspace of V, is by starting with some basis of W, and then asking whether this basis spans V. If it does not, simply add some V1 outside the span of W1 to Wm, and then, if possible, add some V2 that's outside the span of W1 to Wm and V1, and continue until we get to some basis of V. So this entire thing now is a basis of V. And now from our previous intuition, you would suspect that when we mod out by W, such that these W1s to Wms all become zeros, then V1 mod W all the way to Vn mod W out to be a basis of V mod W. And of course, if that's true, this equation is verified, and I leave this up to you to check. And to no longer digress and go back to this natural isomorphism, what this is telling us is that if V is finite dimensional, dimension of V minus dimensional kernel of phi is equal to dimension of image of phi. And of course, this is exactly the rank nullity theorem once again. Now I want to finish by talking about a very beautiful, elegant way of defining an object called universal property. To illustrate this, I want to once again go back to the example of external direct sum. And I want you to observe that if you have an external direct sum V plus W, then we have this very natural projection maps from V plus W to V and also from V plus W to W, simply given by projecting V, W to V and V, W to W. So let's call this projection maps pi1 and pi2. And now what I claim is forget about how we defined V plus W. Forget about what this projection map actually is. I claim that we can just define external direct sum by considering the tuple V plus W, this linear map pi1 and this linear map pi2, and specifying what kind of property the space pi1 and pi2 satisfies. I claim that we don't even have to know what V plus W actually is. And how we can proceed is as follows. Note that for any vector space U, and for any linear maps going from U to V and U to W, say phi and phi prime, there is a unique linear map. So there is a unique linear map, say psi, going from U to V plus W, such that if you apply psi, then you apply pi1, that's going to be the same as applying just phi. And such that if you apply psi, and then you apply pi2, that's going to be the same as applying phi prime. So here is the summary of the universal property, in which every map is linear. And now I want us to think about why this actually defines the external direct sum that we are used to. Well, remember that in the original external direct sum, when we had our projection maps defined in a very natural way, suppose that we have a vector space U and we have these linear maps phi and phi prime. What should our psi be? Well, since an element U is being sent to phi of U here, and it's being sent to phi prime of U here, our psi has to be the map that sends U to phi of U, phi prime of U. So that when we compose it with the projection maps, then we are going to exactly get phi of U, and we're going to get phi prime of U. So we see that our original external direct sum actually satisfies everything, so this is good. But the question remains, what happens if I give you any random space that we're just gonna call V plus W along with these special projection maps, such that this entire property happens to be satisfied? How do we know? How do we know that this is in fact the same space as the external direct sum that we are actually used to? There is a very beautiful way of doing this. Let's say we have one external direct sum, and let's say we have another external direct sum. So let me denote it as +1 and +2, and we have this projection maps pi1 prime and pi2 prime in this universal property for the second external direct sum as well. Then we know by the universal property of V plus 1W that we have this map psi, but we also know by the universal property of V plus 2W that we have some map, say psi prime, going the other way. And we would be exceedingly happy if psi is an isomorphism. That's what we are hoping for. To see this, first realize that when we apply phi, then we apply pi1, then this is pi1 prime just by universal property. And analogously, we can see that pi1 by universal property of V plus 2W is going to be pi1 prime composed with psi prime. So we know when we compose this, with psi, we're getting pi 1 prime. And similarly, you can show that pi 2 prime composed with psi prime composed with psi is pi 2 prime. And we really want to say that this map is in fact an identity map on V plus 2W, but it may not be immediately clear why that has to be the case. And to finish off, and this is a really nice proof technique, is to observe that if we have a V plus 2W here, and we also have another V plus 2W here, and we have of course the maps pi 1 primes to V and W, then we know from these two equations that if you consider the map psi prime composed with phi, then the universal property is exactly going to be satisfied. When we apply psi prime composed with phi, and then we apply pi 1 prime, we do indeed get pi 1 prime and so on. And similarly on the right hand side. But of course, if you consider the identity map on V plus 2W, and identity map also makes the universal property satisfied, because when we apply the identity map and we apply pi 1 prime, that's of course going to be pi 1 prime. And similarly on the right hand side. And since this arrow here has to be unique, that's telling us that psi prime composed with psi is in fact the identity map on V plus 2W. And similarly, by starting with pi 1 prime composed with psi prime instead of pi 1 composed with psi as we did here, you should be able to show that psi composed with phi prime is also the identity map, and that of course concludes the proof that psi is in fact an isomorphism, exactly as we wanted. Of course, the natural question is, can we do something similar for the quotient space? Can we come up with an universal property definition for quotient space? And the answer is of course yes, and I'll give you the definition as one of the problems for this episode, and I'll ask you to explore the definition there. Anyway, I hope you enjoyed this episode, and I hope to see you in the next episode.